Hey guys, we already talked about a irreducible representation of finite group, a finite abelian group. So let's work in some standard example. So I plan to do the example like the character table. So for I think for S3 and S4, and also D8, and then maybe A4 in this video. Yeah. So my whole point is to prove give the character table for this. Okay. And remember that we already talked about abelian group, right? So the simple non-abelian group is the character table for the S3. Okay, so yeah, I think this is the standard results that you guys can see the textbook. So let me just follow the standard. So symmetric group has what? Symmetric group has, I remember that the number of the conjugate class is the same as the number of the irreducible rep. Right, so for the S3, we total have 6 elements. So it's sum over irreducible, right? So you can check it should be 1 square plus 1 square plus 2 square. This one is obviously, right? This is trivial. And then this should be sign. So, and then this is what we're gonna to find out. Okay, so character table for S3 should be very simple, right? So we have the trivial class 1, and the 1, 2, and the 1, 2, 3. So 1, 2 has 3 conjugate C class, like 2, 3, 3, 1, and this is 1. Remember, we already in the group theory, we know that the conjugate C class is just the different partition of the, it's just the number of the partition, right? So 1, 2, 3 is only contains 2 because it has 2, 3, 1, right? So it's partition. Okay, and we have one. We have 3 irreducible representation. So let's find out the character. Okay, so first one is trivial, right? So everything is 1. And we get another called sign, basically which map each which map the odd permutation to be -1. So it's -1, 1, 1, right? So this just the right dimension. Dimension is here, right? So the rest is 2, right? Because we know that there are 3 conjugate C class, so it should be 2 of them. Okay, so the dimension is 2, right? So let's say this is A and B. And then we use the orthogonality, right? So remember that G belongs to G. Your chi IG, chi JG is just G, right? So and the delta IJ, right? So these two is let's say we use these two, we get a 2 plus 3A plus 1B 2B 0, and then we use these two, we get 2 plus minus 3A plus 2B is 0, right? Which tell you that A is 0 and the B is -1. So it is 0 and the -1. Okay, so this just complete the character table. Okay, so this is one method. So let me talk about the method 2. Okay, so the method 2 is really like the tool that we need to do when we go to S3 to S4. So remember that we talk about the regular representation, right? So we have a so-called regular. So the regular expression, I already say that the character is only at identity is the 3, right? So the rest are I think for the character 1, 2, it's basically it's just character of 0, 1, 1, 0, 0. So it is trace, right? So 1, 2 means that you flip the 1, 2, right? So it's 1. And if you get 1, 2, 3, there's nothing, everything changes, right? So it's 0. So you get 3, 1, 0. Okay. And if you take the inner product, you get 1 over 6, 3 squared plus 1 squared. Remember that there is 3, right? So you should times 3. So which is 2, right? So it's not the same as 1. So that means chi is reducible. Okay, so that means chi is the sum of these, right? But chi is 3 dimension. So the only possibility is that chi should be these, sum of these, or sum of these, right? But we know that this regular should contains the trivial representation. The reason is that if you take the expression like like 1 plus 2 plus 3, which means let's say this is let me just write down. So S3 you can view as a permutation of 3 words. So let's say the permutation is let's say I've permutation as ABC, right? So I can produce a vector called V is A plus B plus C. So your regular expression, right, will fix V, right? Because for any group G, because you just permute it. So that means it contains at least one dimensional irreducible representation, which is spanned by V. And that representation will be trivial because every group econ is the same. Okay, so that means what? That means in your original group representation, you can write as this. The tree. So dimension 1 1 2, right? So you get 1 1 1 1 minus 1 1. So this guy and this guy, their addition, right? Their addition should give you the regular one, right? So regular one is 3, and then there is 3 and 1 and 0, right? So 3 minus 1 is 2, right? 1 minus 1 is 0, 0 minus 1 is minus 1. Okay, so this is the second derivation of the character table of the symmetric or permutation of 3 words. Okay. And yeah, that's it. Okay, so that's working on the how about S4. Yeah, there are many ways to so S4 will be a little bit difficult. So that's working on it. So we get dimension. So let's write down the conjugacy class. So we have 1 1 2 1 2 3 1 2 3 4 and 1 2 3 4. And how many of it is just 1, right? How many of these 1 2? So remember the number of 1 2 is just you choose 4 choose 2, right? So it's 6. And this is 4 choose 3, which is 3. This is 4 choose 1 2 3 4, right? And then you need to take this is 8. I'm stupid. Yeah. And let's see this. So this is you can choose 1 2 3 4 1 3 2 4 1 4 2 3, right? So there are 4 of them. And there are 24 of them, right? So the rest should be 6. Let me see why this is 8. Because you can choose 3 of you get 4 of them, right? You get 1 2 3 and 1 3 2. So for each you choose 3 from 4 and each of them counts 2, right? So it's total 8. So we have 5 irreducible representation. And the first one is trivial, right? And so this is trivial. The second one is called a sign, right? So sign is 1 1, and the 6. This is the odd permutation, so it's minus 1. This is the even permutation, so it's 1. Odd is minus 1, so I think this is what? Yeah. So this 1 2, right? This is the odd times odd, so it's even, right? I guess this is minus 1. This is the odd permutation. Okay. Okay, so we have another representation. So it looks like we have done, right? We don't have, so we still don't know the 3, right? Okay, but the key idea is that I just say that, right? I can consider a regular expression which is 4 dimension, right? So at the regular expression, our character will be let's say with some regular, right? So for regular, this guy will be 4, and this 1 2, right? This 1 2 will be fixed. Will be this 1 2 is changed, right? So only fixed 2 3 and 3, 2 and 3 and 4, so it's 2, and then it's only fixed 4, right? So it's 1. This is just 0, right? 0 because everything changed. And then your regular minus trivial will give you another representation. Let's call U, which is 3 minus 1 and 1 minus 1 0 minus 1 minus 1, right? So this guy is irreducible. Okay, so once we notice this, then our dimension, right? Our dimension is 1 1 3, right? So So you know that your dimension 1 squared plus 1 squared plus 3 squared plus c squared plus d squared equals to 24, right? So your c squared plus d squared should be 1 plus 1, which is 2 plus 9, 11. So should be 13, right? So you can easily say that it only is 2s3, okay? So the rest should be there is another 3-dimensional one and also the 2-dimensional one, okay? Okay, but we know that I already there is a fact that I think I also mentioned that if you have an irreducible representation and then you tensor any 1-dimensional representation, then it will give you another irreducible representation. The reason is that the reason is that this guy is 1-dimensional. Okay, so if you tensor product another 1-dimensional representation, which will give you will give you another one. Okay. So once you know this, then you can tensor sine and then with this guy, right? And then you get another one. So it's this guy times so 0 times minus 1. Okay. So this is not okay. So this is the final one that we don't know, right? But actually we have 4 equations. We can add the A, B, C, D, and then we try to solve all of them. And then this is your exercise, right? Because finally we can just use the orthogonality to predict 4 of them, right? Because we have 4 of them and we have 4 equations. 1, 2, 3, 4, right? And also orthogonal, right? So it's enough to get the answer. So answer, let me just write down. Okay. Okay, so this is the results for the current table of S4. Okay, let me see. Maybe let me just talk about quickly talk about let's see. So let's quickly maybe talk about the D8. Maybe I left for the S4 in the next video. Okay, so let's working on a D8. Okay, so the D8 is the group of the permutation of the square, right? So basically it's this, and there's a rotation called R and the reflection called S. So I think everybody knows about the answer, the definition, right? So D8 is generated by Rs, and the R to the 4 is S squared plus 1 equals 1, and RS R minus, sorry, SRS minus should be R minus R inverse, right? So this is the standard representation, and there are total 8 elements, which is R squared, R cube, identity, and SR squared, SR cube, and S. Right, so total with 8 elements. Okay, so the key step is just very easy. We just try to find its number of conjugate C class. So let's compute the number of conjugate C class. So remember that G conjugate to H if G is alpha H alpha inverse for some alpha in the group G. Okay. Should be very simple. Okay, so okay. By the way, obviously DA is non-abelian, right? Due to this property. Okay, so let's see why this guy is how many conjugate C class. Okay, so let's quickly see. So S inverse is R inverse, right? So which take you the first conjugate C class, obviously, because so R and R cube, which is R inverse, are the same conjugate C class, right? And identity is its own conjugate C class. How about R2? Okay, how about R2? Okay, so notice that let's see. Okay, so let's see. Let's see. So then one can easily compute. Let's say R inverse is S inverse R inverse, right? So this is just S to the R cube, right? Because S inverse is S, right? R inverse R minus 2 is R2, right? So that means what? That means S is the same as SR squared, right? Just this is just the same as, so S is the same as SR squared. And also these two, right? So also easy to show that SR, right? So let's check. So RSR, R inverse is SR cube, right? Because just using the rules, because these guys are the same as RS is S inverse R inverse, right? So which tell you that these two are the same, right? So we have these, the first conjugacy class, second conjugacy class, third conjugacy class, fourth conjugacy class, and the 5. Okay, so there are 5 then, 5 conjugacy class. So the conjugacy class, let's just write down the conjugacy class of D8 will be identity, and let's say identity use 1, and the R, which is the same as R cube, R square, and the SR is the same as SR cube, and SR square, which is the same as S, right? So total 5. Let me see. So 1 R square, and you can use S, or basically S and SR. Okay. Okay, so now let's write 5 of them, right? So we get 8 equals to 1 squared plus A squared plus B squared plus C squared plus D squared. So 7 equals to sum of the 4 squared, right? And you know this guy is non-abelian, so at least one of them should be 2, right? Cannot be 3, right? 3 is 9 is over, so D must be. So if I choose the largest to be D, then let's say I choose the largest to be D. So let's say D is 2, then A squared plus B squared plus C squared, which is 3, right? So it's 1, 1, 1. Okay, so let's write down a table, right? So table should be looks like 1 R and RS. So this is R squared and RS and S, and the number of conjugates number of the elements 1 and 2, 2, 2, 1, right? Okay, and then the dimension, which is I already proved, is 1, 1, 1, 1, 2. Okay, and then this is trivial. Okay, so it seems like this is all we know, right? But actually, there's a easy representation for this, right? If you just quotient D, if you quotient D8 by the subgroup of these, right? There's a sub here. There's a there's an index subgroup, right? So right. So there's an index subgroup. So let me see. Okay, so let's maybe change another way. So let's see. So this row, let's compute it. So this is 1, 1, 1, 1, 2, right? So let's compute this row R, right? So the property of this row R is that R4 should be 1, right? So your row of R to the 4 should be 1. Okay, so row of R should be the 4 should be 1, right? And also this S squared is 1, right? So your row of S squared should be 1. So row of S should be plus or minus 1. Okay. And okay. So you have this, right? You have row S squared, row R4 is row R to the power 4 is 1, and the row S squared is 1. And then you also have the row S, row S is row R inverse, right? So this relation tell you that row S should be plus or minus 1, right? But if row is okay, so let's pick row S is 1, right? So you get the row R, you get the 1 and 1, so you get row R equals to row R inverse, right? So you get row R squared equals to 1. So row R actually is plus or minus 1, right? So you see there are total 4 of them, right? So the only way to put, because I already know there are 4 reducible representations, right? So the only one, once I fix R and S, then R squared and R's are already fixed. So the only way that I can make there are 4 distinct one are picked to be are picked to be -1 and 1 -1, right? And S also can be four choice, right? So uh S can be -1, -1, 1, right? Because so from this proof that we know that the S can only have two choice, ±1, R can only be two choice, ±1. But once I fix all of these, then you already fix all these particularly irreducible representation. So the only way that I can make there are four distinct, then the only way is that I just choose R to be ±1, and there are two of them, and S can be two of them, right? So the effects. So this is what we have. Okay. Okay, so let's fill the rest, right? So rho R square is simple, right? Rho R square is just rho R to this, just R square, and the R is just R times S. So it's okay. Yeah, so these are everything you know for the four of them, right? So the rest is to find the four unknown. Okay, so I think to find the rest unknown is simple, right? You just need to use orthogonality. So you can easily check that this is -2, 0, 0, 0. Okay, let me just, so 0 is obviously, right? Because every guy of these should, I guess is different. I mean, oh, by the way, you can check by yourself. Right? So basically, this is the results. Yeah. So the one can easily construct this irreducible representation, right? Because DAs already have the clear picture of these. So actually, the S can be just reflection, right? So I can choose this. I guess it should be 1, 0, 0, -1, right? And the R can be used to be the 90-degree rotation, right? So I guess it should be can be -2, I think. Oh, sorry, I'm stupid. Sorry, this should be 0. -2 should be here. Sorry, I'm stupid. Yeah. So R can be chosen to be the rotation, right? So it can be chosen cosine 90, sine 90, sine 90, cosine 90. Yeah, my sign here, right? So it's you can get it 0, 0, 1, -1, right? Then you square it against 1, 0, 0. This, right? So this is R squared, it can be -2, and R can be 0, and the S can be 0. Okay, so this is the geometrical points, right? If you see this, then you write down an easy to prove by directly this is irreducible. Okay, so these are all the S4 and S3. Okay, so let me just finish the A4. Okay, let me just finish the A4. Okay, so let's just add a page to get A4. Okay, so there are many ways to get the irreducible representation of A4. But I think the quickest way is that I think the quickest way is to reduce the. So I think the quickest way to get the A4 character table is to reduce from S4, right? So suppose you have some irreducible representation in S4, and then you reduce into A4, and there's a chance that some irreducible representation will be reducible in a smaller group, right? Because you reduce your symmetry. But most of the case that yeah, so we can just reduce all of it into the A4 table, and I think once we did this, then we can get an answer. Okay, so let's just write down the A4. So this is A4. You're going to get the identity and also the two. So the original odd even permutation, right? So this is odd, right? So this guy this guy is even, right? So this guy is even, and yeah, so but remember that in this guy that 1, 2, 3, in the conjugacy class in the S4 they are conjugate, right? But in the A4 they can be different, right? So these two are different, right? So that means you get 1, 2, 3, 4, and the 1, 2, 3, and the 1, 3, 2, right? So the number of them is 1, right? And these guys is still 3, and then you get 4 of it, 4 of it, 4 of it, right? So these guys splits into 2, and then you have the dimension. So get the first one is 1, which you don't know the rest, right? But it's 1, 1, 1, 1. So you see, in this case, that the first trivial and the sign representation reduce to the once you reduce S4 to A4, right? These two reduce to the same. So -1 become 1, right? Because in the sign there's no this odd permutation. Okay, but let's say how about this? How about these three reduce? Okay, so remember that we have 12, right? 12 is the same as a squared plus 1 plus b squared plus c squared, right? So you get a squared plus b squared plus c squared equals to 11. So let's see what solution you can get, right? Suppose you get 1, you get the b squared plus c squared equals to 10. And it's possible, right? It's 1 and 3. Okay, so easy to check that this is the only case. If a is 2, you get 4, right? So b squared plus c squared equals to 7. There's no way that a 2 square of integer equals to 7. So the only case is 1, 1, 3. Okay, so we should just easily put 1, 1, and 3. Okay, but by definition, these 3 must come from this guy, right? Because this is 3 dimension. So once it reduces, the dimension must decrease. So the only way is that these 3 must come from S4. Right, and you see that actually it's the same if you do not count this -1, right? Because this is odd permutation, which is already eliminated in A4, right? So once we did this, we get I think this is 3 and then -1, 0, 0, right? So you see this 1, 2, 3, 4 just inherited this -1, right? And this 1, 2, 3, 4. Sorry, this 1, 2, 3, and this is just still 0, right? So just reduce. Okay, and then this is 1, 1. Okay, so the rest is just very simple to find all of the 3 of them, 3 number of them. Okay, but let's see. So now we already know this guy, right? This guy already get reduced to we know what way reduced, right? But how about this? So this guy should also be reduced, right? So this guy should be also be reduced, like so there should be, so this guy, which is let's just write down, so this guy should be reduced to 2, and so it's -1, and also 1, 2, 3, 4 is 2, and 0, 1, 2, 3, sorry, this is 2, and the 1, 2, 3 is -1, right? So it's -1. Okay. Okay. So you see, this guy, right? This guy should be reduced. Should be reduced to it, right? So now these 2 dimension must be sum of the 2 irreducible. It cannot be 2 trivial, right? Because 2 is not the same as -1, -1. Okay, so there's a possible way that these 2 is sum of it, so sum of it or sum of it, right? So there are only 3 possible cases. Okay. Yeah, so you can check by yourself that you can try to get the results. So let me just write down the results, which is this guy. This is 1, 1, and omega square, and omega square omega. So actually, this guy is just sum of this guy, right? So that the omega plus omega square is -1. So 1 plus omega is 0, and omega is -1 plus square root of 3i divided by 2. Okay, so actually this is the answer. Yeah. So this is the one way. Okay, so in the second way that let me just quickly mention. So the second way is that you try to, you know that there is a subgroup. There's a subgroup inside A4, right? So it's the same as what we are doing in the D8. We are doing the D8. So you see this 1, 2, 3, right? So You row 1, 2, 3 is just some number A, right? And you know that A cube is 1, right? So the only way is that this A is just can only be what? Can only be 1 or omega squared, right? So this is the case, right? But you know that let's see. Right. So this is the possible results, and you can check that once you get this. I think there's a results that say what? Say that the A4 character, the A4 is generated by the every even. It's like a 3 cycle, I guess. So I mean, once you define this 1 omega square, then you can easily put in this. Okay. Or basically put in this, right? But once you put this 1 and omega square, then you can easily get the rest. Yeah, so this is usually the easy way to get the A4 character table is to reduce from S4, right, to A4. Right? But once you can do the same calculation for this guy, and use, since it's one dimension, right? So you can easily guess that these guys are roots. Otherwise, that if these guys are all 1, then it's the same as this. So the only way for this is omega and omega squared. Also notice that these guys square needs to be 1, right? So there's only -1 and -1 here that you can put, but you cannot put -1 and -1 here. Otherwise, that these two guys cannot. There's no way that this reduced representation can be sum of the two. So the only way is that there should be another guy which is 1 here. But this is if 1 is here, then 1 must be here. Then if 1 is here, then you can easily get this omega squared to make the orthogonality. So what I just want to say that the character table is highly restrictive. So there's multiple ways to get the A4 character table get the character table for a small group. Okay, so in this video, we finish the S3, S4, and the A4 and the D8, and in the next video, we work in the more larger group. See you guys next videos.